Welcome back. I'm flipping. I'm going to make you flip. Watch me flip markers for 10 minutes. Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here. Hit the notification bell. You'll get notifications for this series and a bunch of others on our channel. We're doing linear algebra. Now I can try to do it. Yeah. Chapter 1, we're doing systems of linear equations. Section 1.4 is going to be 2 equations and 2 unknowns. And then don't worry, we're not going to have a million sections of doing all the cases. 1.5 will be m equations in n unknowns, and then we'll do the general scenario. Then we'll give you all the definitions of what's going on in the general cases. But today, what we're going to do in this lecture is solutions to 2x2 linear systems. And I even put it on the title this time. You're going to hear me say it a lot. There's always one solution, no solution, or infinitely many solutions. And we'll give a geometric interpretation to why that is the case. Let's do that. Okay, what we've done is discussed a single equation and then added more and more variables. We now have a systematic way of saying if you have m unknown variables. I got cats destroying stuff in the other room now. I really want to go check, but we're going to focus. We're shooting videos. Thus far, we've looked at one equation in n unknowns, and if we keep adding those n unknowns, we're assuming that you have n unknowns, so all the coefficients are non-zero. So what we're doing is moving them to the one side of the equation, dividing by the coefficient in front of the first variable, and then we're saying here's the general solution. We make a bunch of free variables, and then we can't have a unique solution, so we have the general solution, which we showed last time. Now what we want to start doing is looking at more than one equation, and so we need our first new technical definition. And what a system of equations is m linear equations in n unknowns. So we've already looked at the n unknowns, but now what we might do is possibly put those n unknowns in m different equations, in m different rows. And that's what we're talking about, a system S, they may call it sometimes for simplicity. But when I talk about a system S, you'll see what I mean when I draw this out in general when we have this. But for now, what we're going to do in this video is just use this technical definition and look at a system of 2 equations in 2 unknowns. And then we'll get the idea of seeing that there's always going to be one solution, no solution, or infinitely many solutions. And we'll get that nicely with a 2x2 system in this video. And then we'll go on to the general m equations in n unknowns. But for now, a system of m linear equations in n unknowns is simply just a set of m equations in those n unknowns, each of which happens to be a linear equation. And what does that mean? I remind you just in case. A linear equation in n unknowns means that every term, a term is something separated by plus, minus, or equals, not multiplication. These are terms, term, 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 term. And there will be pluses in between them or something. So if we have plus and then minus and then minus and then plus, this is a term, and this is a term, this is a term, this is a term, this is a term. This one's linear because it's a multiple of a single variable or a constant term. Those are good guys. The bad ones you're looking for, and which we're not going to discuss in this class because we're not discussing nonlinear equations. That'll be another video for some other time. The nonlinear terms that we're looking for to eliminate when we make you decide this is if you have the product of 2 of these terms in there, or if it's the same term, if you take xi times xi, so x squared, all of these things are bad. X squared, x cubed, you can't have any of those powers. It has to be essentially power 1 is what we're looking for. So a single multiple of a single power. As soon as you have those, this is 1 power, 1 power. Is this okay? No, because if you add them, I have the power of 2 variables in a single equation, essentially, if you want to think about it that way. So bad, nonlinear. Bad, nonlinear, and of course if you have any nonlinear function of our variables, this is bad. If you have cos of 1, that is a constant real number, that's a linear term. So this is okay again. So again, recap, we have linear terms and nonlinear terms. A system of m linear equations in n unknowns is simply m equations in those n unknowns, all of which only have these kind of terms in them. Let's do the first case, which is a system of 2 equations in 2 unknowns. 2 equations in 2 unknowns, we're going to start solving this idea, or we're going to start with this idea of solving systems of linear equations with a 2x2 system. What that means is, again, the first one is the number of equations, and the second one is the number of unknowns. Hopefully, in a lot of scenarios, we're going to try and call that a square system where we have the same number of equations as we do unknowns, and that will be the ideal scenario because usually the real world looks for a unique solution, and that will be the scenario we're looking for. However, there's always 3 cases, one solution, no solution, or infinitely many, and we want to find a systematic way of finding which one that is and how we can find all of the solutions to these systems now. So before we start, these are the two avatars algebraically. We're going to get to the geometric avatars in a second, which are much nicer. You'll hopefully agree. We're going to use A, B, C, D, and then E and F for the right-hand side, and those are going to be all constants for simplicity. But it's going to be more and more useful now with the double indexing to see what's happening when I have actually more than one equation to talk about. The first index now in green tells us which equation or row we're in. And then the second index, red, is going to tell us which free variable or unknown variable we have, or which column eventually in this augmented matrix or coefficient matrix is going to tell us the column that we're in once we get more terminology. So we want to know the rows we're in and the columns we're in, or which equation and which unknown variables we're talking about. So this is why we're going to start double indexing, and this will become much more useful in some scenarios. Again, in this scenario, you may have a system that looks like this. C could be 0. But if now A was 0 also, then you have a system of two equations and one unknown y. So we have to have this restriction that some of the coefficients can be 0, but you have to have it in a way that in some of the equations somewhere all of the variables that you're talking about appear. Otherwise it's one less variable you're talking about again. So in these systems we have to have this as sort of the restriction where A or C have to be not both 0 and B and D have to not both be 0 simultaneously. And then that allows us to truly talk about a system of two equations and two unknowns. And then the other definition we're going to have to get to, and we'll recap this in the next video also, but a solution in general to any m by n or a 2 by 2 system is we want to find any ordered n tuple or 2 tuple. In this case we're going to call it an ordered pair, x and y, or x1, x2. And we want to find an ordered n tuple which makes the m equations true simultaneously. This is a subtle difference and we'll go through that in a second, but for a solution to one equation in m unknowns, all we need is an ordered n tuple which makes that one equation true. Now what we have to look for is m unknowns which makes the first equation true and the second equation true, and if you have more, all of them true simultaneously. It can't just work for one of them and not work for one of the other equations. Let's look at what that means specifically in the 2 by 2 scenario. Okay, for our first example, we're going to compare a 1 by 2 system and a 2 by 2 system. What that means is the first one is one equation and two unknowns, and the second system is a 2 by 2 equation, which is two equations and two unknowns. From our previous videos, we saw that there can never be a unique solution to this because there's two variables and we can't narrow them both down. We move y to the other side and solve for x in terms of y. We call y a free variable t, and x is 4 minus t, and this is, again, pictorially, this is the equation of a line in the plane, and every point on that line is a solution to this one equation. Therefore, for example, if we choose t equals 1, we're going to get 1 and 4 minus 1, so the ordered pair, which is a solution to this one of the infinitely many solutions, or a point on that line, is the point x equals 3 and y equals 1. Once I consider that scenario, there's infinitely many solutions to this 1 by 2 system, but now notice that this is the same equation, so now I create a new system by adding another equation. There is no longer infinitely many solutions to this system because the infinitely many points here solve this equation alone, but they don't solve simultaneously this equation we're going to see in a second. So we're going to go through this systematically in the next couple scenes in this video, but what we're going to do is, for now, I'm going to ad hocly quickly solve this 2 by 2 linear system. The idea is when you have two pieces of information, I solve in B. Because I had a minus, it was easier, because I don't like minuses, I made it plus, and then there's no minuses anymore. That's why I chose it. But you can usually you pick either equation, but you should start from the bottom and work your way up, because that's what we're going to do with elimination also. So in the equation B, I solve for x in terms of y. I get 3 plus y. But now I can plug that into equation A. When I do that, x plus y is 3 plus y equals 4. I can now have, this is now one equation and one unknown. I group the y terms together, I group the constant terms together. Classically, we move to the other side, we solve for y, and I get the unique solution to that, which is y equals 1/2. We're solving a one equation and one unknown there. Now, once I have that, I put that in for x, and I now have another equation and one unknown, and I get the unique solution for the x in that scenario, and I get the fact that there is a unique ordered pair, which will be the intersection point of these two lines in the plane, you'll see in a second, which is now the unique solution to this system. This system, long story short, only has one solution, 3.5 and 0.5. 3.5 plus 0.5 is 4, and 3.5 minus 0.5 is 3. It's really easy to check once you have it too. We're going to give you a magic systematic way of getting this answer in the next couple scenes. For now, what we want to do is show you what we mean in that subtle condition in that definition, which says that they have to, these solutions or ordered pairs have to solve the equations simultaneously. Therefore, pick this guy. It is one of the infinitely many solutions to this system. Definitely 3 plus 1 is 4. Check, it works. You can pick any ones you want, 4 and 0, and 5 and -1. There's infinitely many of them. Integers ones, Diophantine type ones, and there's fractional ones too, because yes, 7 over 2 and 1/2 still works too. And you can flip those, that also works. You can also have 1/2 and 7 over half, that one works too. But only this one is a solution to this one. None of the other ones work, because if you try this one, 1/2 minus 7/2 is -3, not 3. So it doesn't work and it doesn't solve this equation, this one. Or if we pick the one that we were starting with, 3, 1, if I do x is 3 and y is 1, that gives me 2, which is not equal to 3, which is what I needed. So it didn't solve the second equation. So it's not a solution to this system, but it is a solution to this system. So when we say an ordered pair is a solution to a system, it has to solve all the equations simultaneously. If I take the one that is the true solution to this one now, what was it? It was the ordered pair xy is 7 over 2 1/2. That's the only one that works. If I put that in there now, in equation A, I check. That gives me 7 over 2 plus 1/2 is 8 over 2, which is 4. It worked, good. And then if I do in equation B, does it solve equation B? I take the same ordered pair and put it in again, and I get 7 over 2 minus 1/2 is 6 over 2, which is 3. It solved both simultaneously. That's what they're talking about. Now let's do the 3 cases of one solution, no solution, infinitely many. I'm going to use this one again. All right, solving 2x2 linear systems. Basically what I'm going to do is magically, I hope you can guess, but for pedagogical reasons, what I'm going to do is one solution, which we just saw, unique solution, infinitely many solutions, and no solution. What we're going to do is couch inside the scenario that in any size system, any number of equations, any number of unknowns, there can only ever be one solution, infinitely many solutions, or no solution. And we can get a nice geometric pictorial interpretation as to what those solutions represent in the plane. And to remind us before we start doing that, to solve any one of these systems, which is 2x2 now, we mean find all ordered pairs x and y, which make both of the equations true simultaneously. Let's do that. Specifically what we get is, in the first one, let's see if I can do this. We're going to do this obviously ad hoc. The whole point here is just to get an idea of what it looks like to have a unique solution, infinitely many solutions, or no solution. We're then going to go on in the next section, use Gaussian-Jordan elimination and row reduction to systematically solve any system to give you the scenario of, in the row echelon form of the augmented matrix, in the last row, I can essentially tell whether I have one solution, infinitely many solutions, or no solution. For now, don't worry about how I'm solving them. Just pay attention to the fact that there can only ever be 3 cases. In the first one, we already did this. In the last equation, I solved for x in terms of y. So x is 3 plus y. I plug that into the first equation. I get 3 plus y equals 4. You group like terms that have one equation and one unknown. That tells me that y is 1/2. Because y is 1/2, I can put that back, substitute that. We're going to call that eventually into x. And that says x is 3 plus 1/2. Which is 7/2. So we get the unique solution. There's only one solution to this, so we get unique. The only ordered pair is xy equals 7 over 2 1/2. That's our unique solution. And you can check at first, if you put those in there, which we just did in the last scene, it solves both equations simultaneously, not just one or the other. So this is the only solution. For the next one, what we notice is, or hopefully you'll start noticing, is like I didn't notice at all, and this is where the key to ingenuity is hiding your sources. So steal it from me. I immediately noticed that this is 1 1 4 and this is 2 2 8. So it looks like what they did was multiply both sides of the equation by 2. And so this is the same equation. So if I take this equation and subtract it from 2 times this equation, then I'm going to get 0 plus 0 equals 0, and I get 0 equals 0, and that's a tautology. And what that means is there was no new information in that system. There's only one equation in this system. In fact, it's not a 2 by 2 system, it's a 1 by 2 system. And what did we learn from our previous videos? If this is the scenario, there has to be infinite and many solutions. What that's going to give now in the scenario of this, we let y equal the free variable, and x is 4 minus y, where t can be any free real number, and therefore we have infinitely many solutions to this. Again, don't worry about how I'm getting these. We're going to get a systematic way of doing this eventually in the next couple of videos. So that's what it looks like to have two equations in two unknowns, where eventually we say we have a free variable and infinitely many solutions. One of the equations will disappear, is what's going to happen, even when we do this fancy row reduction and Gaussian elimination. And then in the last scenario, what's going to happen, if I try this, there's more than one way I could do this. I could do the same move here. What if I subtract the rows from each other? I would get 0 equals -1 or something like this. Or let's just use what Hypatia says, and we'll use the transitivity of equality. I see that 4 equals x plus y, but so does 3. And if I cut out the middleman, that says 4 equals 3. And so what we're really saying is this system has solutions if and only if 4 equals 3. I would hope that 4 doesn't equal 3, and therefore we can conclude that we have no solutions to this system. Therefore, long story short, what we're going to get is the fact that if you get a contradiction where 0 equals non-zero, or if from 4 equals 3, I could subtract 3 from both sides and get 1 equals 0. So if you get something like this where 0 equals non-zero, this is going to be a logical contradiction, and you're going to get no solutions to the system. Again, as you can see, this is the only 3 scenarios we can ever cook up. There can only ever be a unique solution, infinitely many solutions, or no solution. Let's give a geometric avatar to what this is actually saying in the plane. Oh, well, there's another one. Okay. They're all running around outside. It's wet outside because it's raining. This one's Willa. She's messing with stuff in the background. Let's solve the linear systems. One solution, infinitely many solutions, no solutions. You got it? All right. What I'm going to do pictorially is give you a geometric avatar of these scenarios. Quickly, also, I want to squeeze in the fact that these are all straight lines in the plane. So I'm going to revert back to my K-12 knowledge or calculus knowledge, and I'm going to use the y equals mx plus b form and solve for y is dependent and x is independent. In the first system, I see that I have the equation y equals -x plus 4, mx plus b form, and then this equation is, if I move that over, y is x minus 3. For the first one, which I've drawn twice already, but I'm going to do that the easiest way now that I have a straight line is uniquely determined by any 2 points on that line, and the easiest way to find the 2 points is the x and y intercept. If I let x equal 0, I see y is immediately 4, so that's going to give me the point 0, 4, that point on my line. And then if I let now y equals 0, I could move the negative over, and that means x will be 4 also, so that gives me y is 0 and x is 4, and that gives me the 2 points on my line. That says that my line is now that straight line. Well, that's a straight line, if I say it is, I guess. There, close enough. Straight line. Uniquely determined by those 2 points. Now for the next one, if I want x to be 0, then that says y is -3. Oh, see, you didn't prepare enough. 1, 2, 3, there it is, because I said when x is 0, now this time y is -3. And when y is 0, x is +3. Ooh, there it is. And then guess what's going to happen magically? Right at, I need another color, don't worry, widgets always have more colors. Right there, ooh la, there it is. Right at, what is that? 7/2 and 1/2, or this guy is the unique ordered pair, 7/2, 1/2, which is the only ordered pair on both of those lines. It's the point of intersection of those 2 lines in the plane. So now geometrically, what is happening here? If you have a unique solution to a 2 by 2 system, what you're really asking is find all points x, y, which are on both of those lines. If they are non-parallel lines, they will intersect at a unique point, and the unique intersection point will be the point which is on both of those lines and the unique solution to my system. If I have that those 2 equations are expressing the same line, then we really only have one equation and one unknown, and we're expressing, I put them both on the same one because they're essentially representing the same line, and I have infinitely many solutions to this system because any point on that line is a solution to this system. And then if we have two parallel lines in the plane, those are both straight and parallel, because I said. If I take the parallel lines now, these are y equals mx plus b. They're parallel, so their slopes are the same, and they're uniquely determined by their y-intercepts. This is 4 is the y-intercept of this one, and 3 is the y-intercept of this, and never the twain shall meet. So there can be no ordered pair x and y in the plane, which is on both of these guys simultaneously, and pictorially that seems obvious. And so there are no solutions to this system. Again, there can only ever be one solution, infinitely many solutions, or no solutions to a linear system. Next time we're going to generalize this to m equations and n unknowns. Please subscribe right here, hit the notification bell. I'll see you next time.